Swayam Prabha. Digital India. Educated India.
All right, so good morning, good afternoon. Welcome back to our series of lectures on analysis and design of rigid pavements. In this course, we have been looking at the analysis of rigid pavements so far. I'm sure all of you are waiting to actually do some design. That's what you signed up for this course for. That will come up soon. We are only about 2 lectures away from starting our design part of the class. But let's take a pause and understand where we are in the class overall and how did we come to today's lecture. So our entire course is divided into 4 modules. Module 1 is an introductory module. Modules 2 and 3 were the analysis of rigid pavements. Now, Module 2 was analysis using classical methods and Module 3 is analysis using modern numerical methods. Module 4 is the mechanistic empirical design of rigid pavements. Now, Module 4 will start in about 2 lectures from now. But let's talk about Module 1. So, Module 1, I gave you a brief introduction to rigid pavements and I pointed out that there are basically 4 types of rigid pavements that mainly, there are a couple of others, but mainly we're interested in 4 types of rigid pavements. That is JPCP, jointed plain concrete pavements, JRCP, jointed reinforced concrete pavements, CRCP, continuously reinforced concrete pavements, and PCP, pre-stressed concrete pavements. Now, we learned that JRCP is very rarely used anymore and PCP is used for very specialized applications. Indeed, a lot of studies on PCP or pre-stressing, that's actually done in structural engineering, not in pavement engineering, which leaves us with JPCP and CRCP. Now, JPCP by far is the most commonly used type of rigid pavement. It's basically any rigid pavement you see, there's a very high probability that it is JPCP. CRCP is not used, it's not rare to use it. You do find lots of examples of use of CRCP, but it is definitely less used. It tends to be used in very heavily trafficked roads. So, in our analysis so far, we've mainly been considering JPCP. But as we shall see in Module 4, when it comes to analysis, JPCP and CRCP are analyzed in very similar ways. So, all the tools of analysis that we've learned so far, they apply equally to both JPCP and CRCP. It's only when we come to the point of design that the two tend to branch off from each other, and therefore in Module 4 we'll have more discussion on CRCP. Right now we're mainly looking at JPCP. Now, coming to the analysis of JPCP then, Module 2 we learn the analysis of JPCP using classical methods. Classical methods is just a way of saying it's an old method. In fact, at this point it's almost 100 years old. These are methods where basically under certain assumptions, now we'll talk about assumptions in a second, but under certain assumptions, some very, very smart people have developed solutions which are analytical solutions. So, these analytical solutions are basically nice equations. They do not carry any error. These equations can be solved by hand if you want. They could be solved using a calculator. They could be typed up into a spreadsheet program such as Microsoft Excel and you can solve it with that. The key is they do not require any sophisticated computer program to solve. It's relatively straightforward to plug in numbers into the equations and get a solution. Of course, deriving the equations is not very straightforward, but as I said, some very smart people have done it in the past. The first among them was basically Professor Harold M. Westergaard, who gave us Westergaard's methods. So, Professor Westergaard basically considered a slab. He made three assumptions. He made 3 assumptions. One is that a slab is basically sitting on a bed of springs and the springs can take tension. That is, if you pull up the slab, the springs are going to pull it back down. If you push the slab, then obviously the springs are going to push it outwards. That is not what happens in real life, by the way. If you lift your leg up from the ground doesn't pull you back. So, that is an assumption that he made. Second assumption was that he had the load or the footprint of whatever loads are present on the slab are circular in shape. This is not at all true in practice. In fact, if you look at modern tires and the treads that they have, the actual footprint of the tires on the slab is anything but a circle. It's actually fairly irregular and complicated. It goes to the treads of the tire. Nonetheless, that is an assumption he made. And the third and perhaps the most serious assumption that he made that actually leads to a lot of consequences which make it an inaccurate way to analyze JPCP is the assumption of so-called infinite slabs. So what Westergaard's method assumed is that the load, wherever the load is placed, except the joint at which the load is placed, all other joints are very far away from the load such that they're not having an effect on the response of the slab under that load. So Westergaard's theory assumes three loading conditions. It assumes loading at the center of the slab or the interior of the slab, in which case all four joints of the slab are very far away. It assumes edge loading, and that this is the critical loading. This is actually where maximum stresses appear. It assumes edge loading where the slab, where the load is placed at the middle of an edge, which is a joint, and all the three remaining joints are considered to be very far away. And then he assumed corner loading where the load is placed at a corner, that is at the intersection of two joints, and the other two joints or the other corner is assumed to be very far away from the load. Now, based on this, we got certain closed form equations. Subsequent improvements were made. Instead of having a circular load, some new methods exist which allow for a square shaped load. These sort of subsequent improvements were made, but in all cases, the shortcoming of Westergaard's method was the fact that this infinite slab assumption was not a good assumption and can lead to significant overestimation of stresses and underestimation of displacements. And that increasingly became a problem over time. Now, that was Westergaard's method. That Westergaard method is basically a method for individual slabs. What about the joints between the slabs? There are, after all, between slabs, we do have joints, and generally we don't like to leave joints as plain. Our idea in rigid pavement design is we would like to reduce the stress on the slabs as much as possible, and so we usually have some amount of load transfer from one slab to another across the joint. The load transfer, there are basically three mechanisms which are available. One is base friction, which is essentially always present. One is through aggregate interlock, which is present most of the time as long as it's been constructed properly. And the third is using dowel bars, which are in practice, they're very common today in highways, but it's possible not to have them also, but usually they are present. So this third one is dowel bar interaction. So for analyzing dowel bars then, the method that was developed was the Freiberg equations. That was the other major analytical solution that we learned, which is the Freiberg method for analyzing dowel bars. And what Freiberg basically said is the load transfer from one slab to another slab through dowel bars occurs through the compression of the compressive action where the approach slab is pushing against the dowel bar. The dowel bar is then pushing against the leaf slab, and that's how you have a load transfer from approach slab to the leaf slab. And here what we found in Freiberg theory is that the mechanism of failure, which is very rare in civil engineering, is actually a compressive failure. So you have a compressive stress which the dowel bar is applying onto the leaf slab, and that compressive stress, if it's above something called a bearing stress or an allowable stress, then you have failure of the system. Now, these are somewhat empirically defined and these terms are a little loosely used, failure, but that was basically what it was. The key thing to understand in the Freiberg theory, so Freiberg theory has been successfully used. It can be analyzed for a single dowel, it can be used for a system of dowels. The key thing to understand about Freiberg theory though is that it is a method for analyzing dowels and not a method for analyzing dowels and slabs. So Westergaard's theory and subsequent improvements, they tell us how to analyze slabs without any consideration of dowels. Freiberg theory tells us how to analyze dowels without actually understanding any displacements or stresses developed in the slab, besides the bearing stresses. What we do not have through analytical methods is an integrated theory of slab-dowel action. That is, how do slabs and dowels act together as one combined system? Because after all, in practice, these are one combined and coupled system in practice. As it turns out, creating such an integrated theory analytically is actually quite difficult, and therefore it was not really done with any success in the era of analytical solutions. Which brings us to module 3. So in module 3, we have been looking for modern methods of rigid pavement analysis, and that is using numerical methods. In particular, we've looked at a method which is the finite element method. Now, as I've been pointing out, the finite element method is a very vast method. Certainly, in a couple of lectures in a class on pavement engineering, you are not going to become an expert at the finite element method. For those of you with a background in civil and mechanical engineering, I strongly recommend to take a full-fledged class in FEM and understand the principles and uses of FEM. In this class, I'm just trying to give you a brief overview, a sort of conceptual understanding of FEM with a little bit of mathematics. So what we've seen is that in the Freiberg method and Westergaard's theory, neither of them give us an integrated approach to understanding how slabs and dowels are working together as one system. Now, in module 3, we've been trying to use the finite element method to analyze this instead. The basic assumption of the finite element method is basically two assumptions. One is we are no longer interested in solving the solution everywhere. That is, we don't want a continuous solution. We are only interested in getting the solution of the system at a discrete set of points, which we call nodes. And the nodes themselves are connected to each other using elements. So if we have a finite set of points, we have a finite number of elements, and hence the name finite element method. The assumption in the finite element, the second assumption in the finite element method is that our solution is going to be approximate. So in the analytical solutions, it starts with certain assumptions, and those assumptions may not be correct. But it starts with certain assumptions, and based on the assumptions, the solution is accurate in the sense that if the assumptions are correct, then there is no error at all in the solutions. In the finite element method, we do not actually start with those same assumptions. So the assumption of a circular load, the assumption of a tensionless spring, the assumption of very large slabs, we don't make these assumptions in the finite element method. Instead, we assume that there is an approximate solution. So we assume that our solution is inherently going to have an error in it. We just assume the fact that we have an error. And then what we hope is that as the number of these elements increases and becomes very large, the error becomes so small that from an engineering perspective, that is for all practical purposes, the error doesn't matter. So these are the two basic assumptions of the finite element method. So we saw how to use the finite element method for analyzing individual slabs. There we saw something called an MCZ element, which was a rectangular 4-noded element with 12 degrees of freedom. We saw how to analyze it for one element. We saw there we get something called a local stiffness matrix. We discussed what is a global stiffness matrix and how a local stiffness matrix can be assembled into a global stiffness matrix, and how to solve one slab. In the previous lecture, we started discussing how to analyze joints. And we will have a quick review on that in a second, but we started by looking at how to analyze joints. And what we saw is the finite element method is particularly nice because the entire physics of the problem, whatever the differential equation is, whatever the governing laws are, the entire physics of the problem is basically encoded into a stiffness matrix. So if we have one set of physics, which is the Sophie-Germain equation, which is modeling the slab, and we have another set of physics, which we'll talk about today, if we have another set of physics which is modeling the dowel or the interaction along the joints, we can combine both of them by just adding them or assembling them into a global stiffness matrix. And so then we have one integrated system which consists of both the slabs and the dowels, which we can solve together. That is a pretty remarkable thing, which is very difficult to achieve analytically, but completely possible to achieve using the finite element method. And that's one of the biggest reasons why today, as in modern analysis and design of rigid pavements, the finite element method is basically what's used in practice. You will find a few examples of Westergaard's theory and Freiberg theory here and there, but in practice, what is used in design guides, etc., is the finite element method. We'll see more of that in module 4, when we actually look at mechanistic empirical design. We'll look at the American system, which is based on AASHTO. We'll look at the Indian system based on the IRC method. And you'll see in both cases, the finite element method is used very, very extensively. All right. So in the previous lecture, lecture 20, it was part 1 of this lecture series. We looked at the analysis of joints using the finite element method. And we'll have a quick summary, but what we saw is that we basically saw how we can use the finite element method to solve the slab and dowel system as one integrated system. But then we came across one problem, that basically what is the physics of the joint? That if we have a dowel, what is the appropriate physics to use to analyze or predict the behavior of the dowel? If we can understand the appropriate physics, then it's not very difficult to derive a stiffness matrix and then fold it into the global stiffness matrix and solve it as one integrated system. But as we saw last time, coming up with an appropriate physics for the dowel is not that straightforward. So today we are going to learn the most modern implementation of this physics of dowel, which is called the component dowel bar FEM model. It is a particular model which was developed a couple of decades ago, fairly sophisticated. So I'll give you fair warning, this lecture is most likely going to be the most complicated mathematically, the most mathematically complicated lecture of this entire course. Please bear with me. It's not very important for you to be able to follow each and every equation. It's important to understand the motivation behind how these equations are derived. The equations per se have already been implemented in some computer programs that we'll look at in the next lecture. So you don't actually have to solve them and you don't have to derive every equation. You just have to have a conceptual understanding of what the equations are and how are they developed. Okay. So let's recall then how a dowel bar can be modeled. So as we saw that if we basically have a JPCP slab, thus, let me keep it simple and let's say each slab has 4 nodes. So each slab basically has been approximated using one element. It's not a very good approximation to make, but let's make that approximation. So each slab is approximated using one element. Now what we have here is then, what we said was if you want to model the joint is basically an interaction between nodes which are across from each other across the joint. So for example, if I number these here, 1, 2, 3, 4, 5, 6, 7, 8. So nodes 2 and 3 have some kind of interaction between them, and nodes 6 and 7 have some interaction that's across the joint. If we can model that interaction, then basically we have modeled the effect of the joint. If we have a dowel bar in between, so there are many ways to model the interaction. The first way we had seen was, let's just model it as some kind of a spring interaction between the displacement degrees of freedom. So W2 and W3 we said could be modeled using some sort of spring interaction. We saw that that's basically an empirical method. It's actually fairly widely used. I can't say it's not used at all, but it's empirical and its usage has been stretched quite beyond what it was originally intended to be used. So one method we saw, which is a little more mechanistic method, not a little, it's quite a more mechanistic method, is that we model these connections as a beam. So if we can calculate, if we assume that it's some beam, we have to understand what is the meaning of the beam and what is the physics of the beam. But if we model this as a beam, then for a beam we are basically saying that W2 and now theta y2 and W3 and theta y3, these are connected to each other. So this interaction is basically reduced to a 4x4 stiffness matrix because it's 4 degrees of freedom, W2, theta y2, W3 and theta y3. So it's modeled as a 4x4, as basically a 4x4 stiffness matrix, which can be folded into the global stiffness matrix. So here is a little bit more complex example. This is the same thing which I had shown in the previous lecture. So here, instead of one element, which is pretty unrealistic, I basically have a 4-element system on each slab. In which case now I've got nodes 3 and nodes 4 which are across from each other at a joint. Similarly, nodes 9, nodes 10, node 15 and node 16. These are across from each other in slab. And now if I model the slab, if I model this interaction between the nodes as a beam, in particular what I talked about in the previous lecture was, if this is modeled as an Euler-Bernoulli beam, and those of you in civil and mechanical, I'm sure you've all studied Euler-Bernoulli beams. It's basically beams which do not admit any transverse shear because their length dimension is much longer than their cross-section dimension. So if I model this as an Euler-Bernoulli beam, then in the finite element method, the Euler-Bernoulli beam in each node has 2 degrees of freedom, that is the transverse displacement as well as the rotation about the axis, W and theta. So this Euler-Bernoulli as a whole is a 4x4 stiffness matrix. So it can be modeled as a 4 degree of freedom system. And then what I have is that this 4 degree of freedom system is basically connecting these 4 degrees of freedom of the nodes across the joint. So it's connecting W3 with W4 and theta y3 with theta y4. Similarly, W9 with W10 and theta y9 with theta y10, and finally W15 and with W16 and theta y15 with theta y16. So if I have the global stiffness matrix separately of the slabs, which I can then assemble together, then all I have to do is I have to take the stiffness matrix of this beam, this Euler-Bernoulli beam, and I have to just assemble it into that global stiffness matrix at these corresponding degrees of freedom. And then that global stiffness matrix now includes the physics of both the slabs as well as the physics of this dowel bar, which is of the beam, which is a dowel bar which is modeled as a beam, which is connecting these nodes across a joint. Fairly straightforward. But at the end of the previous lecture, we discussed that this is actually a fairly unrealistic way and it does not really represent in practice what's happening. Experimentally also it has been found that this model of just connecting the nodes using an Euler-Bernoulli beam does not work very well. Why? Well, there are a couple of reasons. If you think of that beam again, so it's a dowel bar. Roughly the diameter of a dowel bar is around 25 mm. It's a fair, it could be 32 mm also, but 25 mm is a reasonable value. So we have a dowel bar which is of diameter 25 mm, phi over here. And if you think of the length of the dowel bar, so the length of the dowel bar is basically whatever is the length between these two nodes. The length of that dowel bar is the joint width, and the joint width is of the order of 1 mm or even of the order of 0.1 mm. So it's very, very small. So you actually have a bar which is of the order of length 1 mm and diameter of 25 mm. Recall, an Euler-Bernoulli beam, a beam is an Euler-Bernoulli beam if the length dimension is much longer than the cross-sectional dimension. In this case, that is not the case. The length dimension is actually much shorter than the cross-sectional dimension. So the assumption which we've made over here is firstly that this is not actually an Euler-Bernoulli beam, that this beam is relatively short. It no longer satisfies the condition to be an Euler-Bernoulli beam. One problem. Another problem. This analysis, that considering there is just these nodes connected, it is completely ignoring the fact that part of the beam is actually embedded into the concrete. So we actually draw a true cross section of the concrete. This is what our dowel bar is. The dowel bar is embedded into either side of the concrete. We are only considering this part of it. That is the part which is between these two nodes. We are completely ignoring these effects altogether. Therefore, it's completely inaccurate. And secondly, we are making an assumption here that the beam is of finite length. That's actually not a bad assumption, but you compare it to the Freiberg equation. So if you go back to our equation in the Freiberg analysis, so please go back to that lecture in module 2 and revise it in case this is not seeming too familiar. But in the Freiberg equation, one assumption was that this Euler-Bernoulli beam was actually semi-infinite in length. So it was very, very long, infinitely long through the slab. That is clearly not the case. Our beam is actually finite in length. So we have a finite length of beam which is embedded into the approach slab. We have a finite length of beam which is embedded into the leaf slab. And then we have a very small and finite length of beam which is the overhang part in between. The current physics which we just modeled, so basically what I drew over here in this slide, the physics which I modeled over here does not adequately represent these three parts. And this is why this dowel bar, this Euler-Bernoulli beam based analysis of dowel bars is not actually very realistic. Okay, so what do? Do we have a more realistic model? As it turns out, again around 30 years ago in 1995, a modern model came up, and this was actually called the component dowel bar model. So this was a paper, and we're going to discuss the details of this paper. Again, this is probably the most complicated lecture of all in this entire series, so just work with me as we go along. I'll try to explain everything slowly. So this is published in the Journal of Transportation Engineering. That's actually published by ASC, American Society of Civil Engineers. Very good journal and a very good paper. So published by Guo, Sherwood and Snyder. It's generally called the Guo model after the first author. The title itself is pretty straightforward. It says Component Dowel Bar Model for Load Transfer Systems in PCC Pavements. PCC pavements, rigid pavements, essentially it means JPCP in most cases. The same analysis could be used for CRCP also, but they basically mean JPCP here. Load transfer systems, that's basically just dowels at joints, right? So it's just a fancy way of saying dowels at joints. And then they say it's a model called the component dowel bar model. So really what if I translate the title of the paper into layperson's English, it basically says a component dowel bar model. So it's a model which is called the component dowel bar model for dowels across JPCP. Straightforward, the name says a lot, but then the question is, what is this component dowel bar model? Okay, so, and I'm going to show you a number of equations and screenshots from the paper itself to illustrate this point. So this I had drawn previously, but this is just a better diagram. So what we see here is that this is a more realistic depiction of what's happening with the dowel bars. The dowel bar basically consists of three bars. So you have the slab and you have the bar. But the bar itself actually consists of three components. You have a component which is, let's say, of length L1, and that is the part which has been embedded into the concrete on the approach slab side. So this is the approach slab side. You have the same thing on the leaf slab side, that you have a dowel bar which is of length L2, and L1 may or may not be equal to L2, generally it is, but you don't have to make that assumption. You have a length L2 which is embedded onto the leaf slab side, and then you have a very short length L which is the overhang in between. This is realistically what a dowel bar, a dowel slab system looks like. Now, what we can do is, let's consider this point again, and this applies to every point. So the way we write it here is this point, so you'll see two terms over here, IS, IB and JS, JB. S stands for slab and B stands for bar or beam. So what we have here is this L1 part is basically C to IB, this L2 part is JB to D, and then this part in between we can write as IB, JB. So IB, JB is a part in between which is this very, very small beam. Okay, so what we have over here is that we basically have three parts. Now, at each of the three parts, additionally, we actually have two more nodes. That is, at one node, we can have the displacement of the bar. We can also have, at the same node, the displacement of the concrete at that point. I will illustrate this point further in a few more slides, but just keep that in mind. So again, this dowel bar basically consists of three parts now. Two bending segments. This is just a way of saying that these are Euler-Bernoulli beams. So we have two bending segments, which is CIB and JBD. That's basically this part and this part. These are bending segments which are embedded into concrete. The reason we call these bending segments is because in this case, for these components, the length is actually much greater than the cross section. So for example, the cross section diameter for a typical dowel bar is going to be 25 mm. The overall length of a dowel bar is something around 500 mm, 500 to 600 mm. If we assume, and this width of the joint is typically 1 mm. So if we set this little 1 mm piece aside, let's say our dowel bar overall is, just to keep life simple, let's say it's 501 mm in length. 1 mm is going away to this middle part, which is the joint. So we are left with 500 mm embedded in both sides of the concrete. If we assume that the embedment length is equal, which is not a bad assumption to make, if we assume the embedment length is equal, then if you look at just this component, this left side part of the bar, then basically we have a diameter of 25 mm and we have a length of 250 mm. We have a length which is much greater than the cross-sectional dimension, and therefore we can analyze this part as well as this right-hand part as Euler-Bernoulli beams, which can be written as bending segments. The middle part, however, is a shear bending beam, because for the middle part, our diameter or cross-section is 25 mm in dimension, but our length is only 1 mm, approximately, order of 1 mm. It's only 1 mm in dimension. So we have a bar which is much shorter than it is wider, and that is not an Euler-Bernoulli beam. That's actually what we call a shear bending beam, or more generally, it's called a Timoshenko beam. So one immediate change we can see compared to what we studied previously is that part of the beam has to be modeled as a Timoshenko beam and not as an Euler-Bernoulli beam. That's not actually very difficult to do, as we shall see. In fact, so if you're modeling it as a Timoshenko beam, previously in the previous lecture, and please go back to the previous lecture if you need the equations for it. When the previous lecture I showed you that if you model a beam as an Euler-Bernoulli beam, then basically you have a certain stiffness matrix for it. How to derive that stiffness matrix is actually out of scope for this class. You should ideally take a formal class on finite element method, or for those of you in civil engineering, you can take a class on what's called the stiffness method, and you'll see the derivation of those stiffness matrices over there. But last time we saw a stiffness matrix for an Euler-Bernoulli beam. Similarly, some smart people have already created the stiffness of a Timoshenko beam, and it's basically what this big equation here is. So it's not important for us to derive the equation. It's just important to understand that we know the stiffness matrix for a Timoshenko beam. So if you're modeling that middle part, that L, that segment of length L, which is very short, if you're modeling it using a Timoshenko beam, then still we have 4 degrees of freedom. That is, we have a displacement and a rotation on one node, and so we have W and theta here, and we have W and theta here. So we still have a 4 degree of freedom system. It's just that stiffness matrix is different in this case. And this is what the stiffness matrix is, what you're seeing on this slide over here. Just for notational efficiency, we'll come back to this later. For notational efficiency, I'm just going to write this like this. I'm going to basically break it up into 2 by 2 pieces, and we'll write this as K11, K12, K21, and K22. So these are basically submatrices. So K11 is a 2 by 2 submatrix, K22 is a 2 by 2 submatrix, K12, which is equal to K21, is a 2 by 2 submatrix. So just for convenience of notation, we'll see it will come back to us in a few slides. For convenience of notation, I'm just dividing this into this thing, and so I can write this in this way. Okay, so this picture that we saw over here, this is basically the initial system which has not been loaded. Let's now consider what does the system look like after we loaded it. So after we loaded it, naturally this is the approach slab and this is the lee slab. The approach slab is going to bend, Because of the presence of the dowel, the leaf slab is also going to bend, but unless we have 100% load transfer, the bending is not going to be equal. We're going to have an unequal distribution of the bending between the two slabs. All right. So after bending, two things can happen. We could have a situation that the dowel and the concrete are always in contact with each other. In other words, that we have a rigid contact between the dowel and the concrete. If the dowel displaces by a certain distance, then the concrete will also displace by exactly that much distance. That's one possibility, and that's actually not a very realistic possibility. The other assumption we can make is that the bar IB over here and the concrete IS, they are connected to each other using some sort of elastic connection. So there is an elastic connection, which means that during bending, the concrete can bend to a different length as compared to the concrete, or different displacement as compared to the concrete. And that's indeed what we actually get in practice. So what we see over here is, initially I had 2 points, let me go back here. I had IS and IB, which were basically the same point. So this point I in the slab and point I in the bar were the same point. And similarly, I had JS and JB. Now what I see is, after bending, IS and IB are no longer the same point, that there is some displacement, relative displacement between them. And similarly, JS and JB also, I've got some relative displacement between them. This is what is realistic. This is the more realistic situation, and that's what the dowel component bar model aims to model, just that. So just to put that in more formal terms, if the interaction between the dowel and concrete is assumed to be elastic instead of rigid, and if the embedment length is assumed to be infinite, this is a bad assumption, by the way. If we assume that these two lengths are basically infinite, then we can use the Timoshenko theory from Freiberg's equation to obtain the stiffness matrix. Remember, Freiberg's equation basically made an assumption that this embedment length was basically infinite, and you had some kind of elastic modulus here, which we defined as K naught. You had some elastic modulus over here. If we go with that assumption from a finite element perspective, then we can still do this analysis. So we can model the tiny piece over here is using Timoshenko beam. We can model the rest of it using an Euler-Bernoulli beam, and that Euler-Bernoulli beam is infinite in length, and it's embedded in this bed of springs. And so the stiffness matrix that we get in that respect, if you make these assumptions, can be written in this manner. That is, it's K is equal to KT minus KTT, where KT is this term, where beta is this one over here, and this you've seen before. This is basically, you have seen this particular formulation before. This formulation is basically from Freiberg theory. So if you go back to the lecture on Freiberg theory, you have seen this particular term beta and this exact formulation for the interaction between the dowel and the concrete. So what we have here then, if I just redraw the figure, what we then have effectively is, we have, of course it's very exaggerated, but we have here at each node, we can have, if we model this as a Timoshenko beam, at each node we have the displacement of the bar and the rotation of the bar, but separately we have the displacement of the concrete and the rotation of the concrete. That's at each node. So now at each node we basically have 4 degrees of freedom, and therefore our dowel bar over here on the other side also has 4 degrees of freedom, and therefore if we use this particular formulation, that is, if we use Freiberg theory as a Timoshenko beam and we analyze it as though it's embedded inside the concrete to an infinite length, then we get an 8 degree of freedom system. That is, our local stiffness matrix for just this piece of it is going to be of size 8 by 8. Therefore, we can model the embedded and overhang. We can model the embedded and the overhang parts of the dowel separately. So the embedded part of the dowel, it can be modeled as an Euler-Bernoulli beam as previous, because it's infinitely long in length. The overhang part we can model as of using a Timoshenko beam with 8 degrees of freedom. 4 of those degrees of freedom corresponding to the bar, and 4 of those degrees of freedom corresponding to the slab. Well, that's a problem. So previously, if you saw how we did it with the Euler-Bernoulli beam, we modeled the overhang as just a simple Euler-Bernoulli beam. It was wrong, but the nice thing was it was a 4 by 4 stiffness matrix. It was a very small stiffness matrix. And without going into a lot of detail, the advantage of having that 4 by 4 stiffness matrix was it basically retained the banded structure of the matrix. So our global stiffness matrix Kg, and this is fairly advanced stuff, so I'm not going to go into a lot of detail, it basically had a particular banded sort of structure. And this banded structure could be used, it's actually very important in the finite element method because it helps to speed up the solution. Again, we're talking about very, very large matrices over here. If the matrices have a particular structure, then we can take advantage of certain numerical algorithms to get very fast solutions from them. So as long as we had a 4 by 4 stiffness matrix for the dowel interaction, then this Kg, the banded structure, was still retained. The problem is if we start using this 8 by 8 system instead, then the banded structure also gets distorted. And once the banded structure gets, so first of all, it's 8 by 8. So we already have more degrees of freedom that we have to solve for. We have increased our computational effort. One. Two, the banded structure, when we try to assemble this 8 by 8 matrix into the global stiffness matrix at the appropriate degrees of freedom, our banded structure also starts getting distorted. So we lose this banded structure, we start having elements which are away from the band, and that can significantly slow down the solution. In the finite element method, while we are concerned about accuracy, but we are also concerned about speed. That is one of the major pillars of FEM. So if we lose this banded structure because of this 8 by 8 matrix, then we end up losing speed. That can be quite a problem. And so this particular way of doing it, that is modeling the embedded part as Euler-Bernoulli beams and modeling the as Euler-Bernoulli beams which have 4 degrees of freedom, and modeling the overhang as a Timoshenko beam with 8 degrees of freedom. While this logically makes more sense than what we were doing previously, it leads to these sort of computational problems that we have to overcome. Now, Nishizawa actually in 1989 made a good attempt to overcome this. They proposed, instead of this 8 degree of freedom model for the overhang part, they proposed a 4 degree of freedom overhang model. The 4 degree of freedom model was useful because it could basically, we would not lose the banded structure of the matrix. Our computational effort would still be relatively small to incorporate the effect of the dowels. So Nishizawa proposed this 4 DOF model. It had all the 3 segments. So it had the overhang segment, and it also had the embedded segments. It made the following assumptions. First of all, it assumed that these embedded parts were no longer infinite, that they were of finite length. This is a very, very big change. Previously, all the previous analyses were assuming that these bars are basically infinite in length, and that allowed us to use some fairly simple calculations, which was basically Freiberg's equation. It allowed us to do some fairly simple calculations to analyze the effect. Nishizawa proposed that these lengths are not infinite, they're actually finite in length. That's a pretty big change. And then they assumed that this small overhang part of it should be modeled as an Euler-Bernoulli beam. That was not reasonable. That we just talked about, because this is so small in length compared to the cross section, this is not correct to model it as an Euler-Bernoulli beam. And therefore, finally, coming to the paper that we're talking about, Guo in 1995, basically they took Nishizawa's model, but they assumed that that overhang part is actually a Timoshenko beam and not an Euler-Bernoulli beam. And that then, once they put that together, so what did Nishizawa do? Nishizawa, instead of modeling this overhang part as an 8 DOF system, they provided a way to model it as a 4 DOF system, but it was modeled as an Euler-Bernoulli beam. Instead, what Guo did, they still modeled it as a 4 degree of freedom system, but this time they modeled it as a Timoshenko beam, which is more correct from a physics perspective. And so this final model, which we're going to discuss in subsequent slides, this final model where the dowel is modeled as a 4 degree of freedom system is called the component dowel bar model. And as we shall see at the end of today's lecture, it has been shown to agree very well with experimental findings. It is the modern method which is used in the most advanced finite element analysis methods for rigid pavements. We'll see that in a couple of slides. Okay, so as I said, the overhang part, the basic idea here is that we have the embedded lengths, and the embedded lengths are now finite. So this is L1 and this is L2. So we have some finite embedment lengths, and we have an overhang part of length L, which is modeled as an Timoshenko beam. So these embedded lengths are going to be modeled as Euler-Bernoulli beams of finite length, and this overhang is going to be modeled as a Timoshenko beam. So for the Euler-Bernoulli beam, we could model it with this equation. One change over here. So previously over here in this, let me open it here. Over here what we saw is that we've basically had 8 degrees of freedom because we had displacement for the beam or the bar and displacement for the slab. These were separate displacements, and we were trying to solve for all these displacements. That's what created this 8 degree of freedom system. That at each node we basically had a displacement and a rotation for the bar and a displacement and a rotation for the slab, and that caused certain issues when we're trying to model this. So what Go said is, let's not model the displacement of the beam and the displacement of the slab. Let's instead model the relative displacement between the two. That's quite an insight. So now instead of having to model two separate nodes, we just model the relative displacement at one node using the physics of whatever is the connection in between. Fairly intuitive idea. So the Euler-Bernoulli beam could then be modeled using this equation, which we've all seen in the past. But here W is no longer the displacement of the beam, it's the relative displacement between the beam or the dowel and the concrete. That's one piece of insight that comes out of this. So now, based on that, what we see is we can model it as follows. So now if we say that at each node, we no longer model the slab and the beam separately, but we just model the relative displacement between the two. Then at this node, we basically have W and theta, where these are the relative displacements and relative rotations between the concrete and the bar. Similarly, at this node, we have W theta, this node we have W theta, and then this node we have W theta. So we see each part can be, this is a 4 by 4. So totally we have 4 nodes and each has 2 degrees of freedom, right? Because now it's the relative displacement, so that's why it's 2 degrees of freedom. So we have 4 nodes. Each of these 4 nodes has 2 degrees of freedom, and therefore totally this bar can be modeled as an 8 degree of freedom system. Still not great. We were hoping to get a 4 degree of freedom system that would retain the banded structure of our matrix. So let's see if we can do something else to overcome this. So this particular equation with the Euler-Bernoulli beam, it does have a solution. Now, this solution was given analytically over 100 years ago by Timoshenko, so there's nothing special what they derived. The solution is W of x is equal to a hyperbolic cosine. So this is what cosh is. This is a hyperbolic cosine of beta into x, where x is basically this. This. So x is basically the coordinate system with respect to the face. So what we have is that, so the W of x is equal to 4, it's a summation of 4 terms, it's a linear combination of 4 terms. The first term is hyperbolic cosine of beta x into the cosine of beta x. So you're seeing a combination between hyperbolic functions and trigonometric functions. That's sort of the oddity of the mathematics as it works out. The second is the hyperbolic cosine of beta x into the sine of beta x. Then we've got the hyperbolic sine, the sinh of beta x into cosine beta x, and then sinh beta x into sine beta x. These are the 4 solutions, and then the final solution is a linear combination A, B, C, D. In order to get A, B, C, D, we essentially need to have some additional boundary conditions, and we need 4 boundary conditions. We have 4 coefficients A, B, C, D. We need 4 boundary conditions. The 4 boundary conditions are as follows. So again, this is for the left side of the slab. So this is this left part of the beam. This is x in this case. So this is x is equal to 0. This is x is equal to L. L is the embedment length. Okay. So we can specify, say, at W of 0 is some displacement W naught and its rotation is theta naught. Similarly, at M of 0, we can put some boundary condition is equal to M naught and some boundary condition is equal to P naught. So we assume that some moment and some load is applied at this end, and we apply the corresponding boundary conditions. What we then get is, noting that at the other end, there is no moment which has been applied. If you make that assumption, then at the other end, we basically get this formulation. We write out these equations and we get W naught theta naught, that is the rotation and the displacement at over here at x is equal to 0. This is given by this 2 by 2 matrix into P naught M naught. These are the loads which are applied at x is equal to 0. This is fairly complicated. Now, one piece of notation which the authors used is, for the hyperbolic functions, they used capital letters, and for the trigonometric functions, they used lowercase letters. So capital S is sinh beta L, and capital C is cosh beta L. Lowercase s is sine of beta L, and lowercase c is cosine of beta L. It was just a short notation they use so that the equations don't get very, very unwieldy. And what you see here is this matrix. It consists of S, C, and you've got beta and you've got EIs. It's a fairly complicated looking matrix. It's not important to understand the derivation. It's not actually very difficult. It all comes from this particular equation. So it's not very important to understand the derivation at this point, but you just understand that you have a fairly complicated matrix. One thing that you want to keep in mind here is you have the forces over here and then you have the displacements over here. So what this is, for that embedment length, for that L1 portion of the embedded part of the beam, this is actually the inverse of its stiffness matrix. The stiffness matrix is always Ku is equal to F. So in this case, we actually have U is equal to K inverse of F. So this is the inverse of the stiffness matrix for that embedment length, for that L1, the embedded part. Now, for the right side of the segment, that is, we looked at the left side over here, so we already saw what's happening over here. We were able to generate the stiffness matrix for this part. We have this little overhang over here, which we're going to model as a Timoshenko beam. We already saw the stiffness matrix for that. And then for this right hand side, again we have an embedment, and here we basically, the stiffness matrix for this part is the same as the stiffness matrix for this left hand side. The only difference is we have to just switch our coordinate system. So in this case, our coordinate system was like this. In this case, our coordinate system is going to be like this. So we just have to reverse our coordinate system. In that process, that happens by just setting the load vector as minus P naught and minus M naught instead of the way we were doing it previously. And then we can similarly get the inverse. So we get from here, we got the inverse of the stiffness matrix for the left hand side, for the left embedment part. And similarly, we can get the inverse of the stiffness matrix for the right embedment part. If you know the inverse, you take the inverse of that, and a computer can do this calculation. You take the inverse of that part, and you basically get the stiffness matrix for this side, the left embedment. You'll get the stiffness matrix for the right embedment. We already had the stiffness matrix for the middle part, the overhang part. This was basically coming from a Timoshenko beam. We assemble these together and we'll get us so we have one node here, one node here, one node here, one node here. We'll get an 8 by 8 stiffness matrix, right? Because we have 4 nodes and the 4 nodes have 2 degrees of freedom each. For each of those segments, we have the stiffness matrix, the local stiffness matrix. We can combine them into the global stiffness matrix for this beam or this dowel bar. It gives us an 8 by 8 stiffness matrix. But as it turns out, we can actually do even better. The reason we can do even better is we know one thing about the physics. Again, I'm drawing this. We know one thing about the physics, and that is that if we consider this part, IB, what we call the points IB and JB, if we consider this, then we know that no load is ever going to be applied at this node. This node is basically a free node. It's open it's on the face, and a load is never going to be applied on that node, which means we can write that P at IB is equal to 0, and the moment at IB is also going to be equal to 0. Similarly, P at JB is equal to 0, M at JB is equal to 0. So currently we had an 8 by 8 stiffness matrix. That is another way of saying that we had 8 equations. Now we have 4 extra equations which we can use. So we have basically not equations, these are 4 constraints. We have 4 constraints, and using those 4 constraints, we can actually reduce the number of equations. It's just a bunch of multiplication and addition that has to be performed. I'll show you the final form in the next slide. It's not important, but all you have to understand is we initially had 8 equations that had to be solved, but we had 4 constraints, which are the constraints which I've highlighted here. Because of these, we can eliminate 4 out of those 8 equations, which means instead of our stiffness matrix having to be 8 by 8, representing 8 equations, we can have a 4 by 4 stiffness matrix for the beam. And that is precisely what we wanted in the past. We wanted a 4 by 4 stiffness matrix, and that 4 by 4 stiffness matrix then allows us to take advantage of the banded structure of the matrix and have a fast solution. So what is this 4 by 4 stiffness matrix? Again, it starts from an 8 by 8 matrix, and then we apply 4 constraints to eliminate certain terms. And that 4 by 4 stiffness matrix is a little bit complicated, I'll admit. It basically looks like this. Okay. It's not, as I said, it's not important to understand how it's derived. I had mentioned it's basically you have some equations, you have some other equations, you start subtracting them to try to eliminate some terms in the equations. All of you have probably done that in high school. You probably haven't done it a little systematically using linear algebra. But if you do it systematically using linear algebra, you will get some terms like this. So what we have over here, we have some I and I2 by 2. So I2 by 2 is the identity matrix. So I2 by 2 is basically 1, 0, 0, 1. So we have basically an identity matrix of size 4 by 4. And from there, we are subtracting some terms which are consisting of some K11, K12, as well as something called a T1, T2. And similarly, we have some matrices which consist of T1, T2. T1, T2 is actually, if we go back to this, what I define this as the inverse of a stiffness matrix. And therefore, the stiffness matrix itself is actually T1, T2. So basically, K inverse is, or if I define this as T, if this is K inverse, then basically T is K. So T in this case is equal to K over here. And so this is what T1 looks like. Fairly complicated looking, but it's actually not too difficult. You're just inverting a 2 by 2 matrix. That's actually quite simple to do. So this is what T1 is, and similarly T2 for the other side of the overhang. Here, by the way, you see this S1, S1, C1. So we had previously defined over here S is this. So if we substitute L is equal to L1, then we simply write S is equal to S1. So S1 is basically sinh beta L1. And similarly, lowercase s1, lowercase c1, lowercase capital C1, and similarly for L is equal to L2. That's basically what these additional terms are. So fairly complicated, mathematically involved, but it's just a number of substitutions and a little bit of notation which is being made. What you will also see here, we had this K11, K12, that I had defined previously way back when we looked at the Timoshenko beam. So at the very beginning of today's lecture, when I had the Timoshenko beam, I then just shortened it into this K11, K12. So what you see here is that the two embedded parts, their physics is modeled by this T1 and T2 matrices, and then the physics of the overhang part, which is the Timoshenko beam, that was modeled by this K11, K12, K21 and K22. All of those are coming together in this one single stiffness matrix, which is of size 4 by 4. How do you know it's of size 4 by 4? Because T1 is of size 2 by 2, T2 is of size 2 by 2. So this overall matrix is of size 4 by 4. And similarly, I2 by 2 is 2 by 2 and I2 by 2 is 2 by 2. So this whole thing is a 4 by 4 identity matrix. 4 by 4 into 4 by 4 matrix gives you a 4 by 4 matrix. So this stiffness matrix is the stiffness matrix of the component dowel bar model. Again, not very important to understand all of this. I'm showing you it's a fairly complicated thing. The finite element method is fairly complicated, but it does allow you to solve a lot of problems that are otherwise very difficult to solve. So this 4 by 4 stiffness matrix is the stiffness matrix of the component dowel bar model. It consists of two embedded parts which are modeled using Euler-Bernoulli beam theory, as well as one overhang part which is modeled using a Timoshenko beam. And certain additional constraints are applied to eliminate certain degrees of freedom. And so with that, we get this overall stiffness matrix, which is of size 4 by 4. Now we already have our slab. Going back to original problem, now we have our slab. Our slabs were divided into several parts, and therefore we had several nodes. And we knew that between the nodes, we had to connect it using something. And now we have our 4 by 4 stiffness matrix for the component dowel bar model. We simply connect the corresponding degrees of freedom. So we still connect W if this was 3 and this was 4. We still connect W3 and W4, and we connect theta Y3 and theta Y4. Just that the stiffness matrix which defines the physics of the connection is a fairly complicated one, which is the one over here. But again, it's been implemented in a computer model already, so it doesn't really matter how complicated it is. But it's fairly easy for us to take this 4 by 4 stiffness matrix and just assemble it into the global stiffness matrix at the corresponding degrees of freedom. All right, so all that seems well and good. It's very mathematical. So if you look at the previous lecture when we started on joints, very, very mathematical, and we kind of talked about the pros and cons using mathematics and sort of qualitative analysis of physics. Similarly, so far we've been talking about qualitative understanding of it should behave like this, it should behave like that, and then the mathematics has been fairly involved. The question which as an engineer you should always ask is this correct? Is it actually representing what's happening in real life? That if I conduct some experiments, if I go to the field and do some measurements, is this actually what I'm measuring? And that's exactly what Gore did. So what they did is they actually went ahead and did a number of tests. And I won't go into the discussion of the test. It is explained in the paper, so you can go and look at the paper to fully understand it. By the way, the paper should be available from your local university library. So try to get a hold of the paper. It's a good paper. Okay, so basically they conducted a large number of tests. And I'm not going to go into details, but what we see here is they have this hatched line over here. That is their test information. And then they've got these solid lines, which is based on the analysis, which was just discussed. And you'll see the agreement was pretty good. The values are fairly close to each other. Of course, there's some difference, and any model is going to give you some amount of error. Again, the finite element method itself starts with the assumption that there's an error. So we're going to have some amount of error, but as you can see, the error is small. And so the component dowel bar model is actually not bad. Now, what I haven't shown here, but it is in the paper, if you don't use the component dowel bar model and instead you use one of the older models, Nishizawa's model, if you use just a plain Euler-Bernoulli beam, the errors are pretty massive. So compared to the errors there, the errors in this case are very, very small. I would argue, although I can't prove it at this point, I would argue that these errors are actually negligible. The point was in 1995, they had only so much computing power. Even solving a 75 by 75 matrix was a pretty tough thing to do in the 1990s. Today, we could probably have a much, much finer mesh, and I'm fairly sure that when you just put a much finer mesh and apply the same component Dalbar model, your error will essentially vanish into some very negligible number. So although you're seeing a somewhat of a largish looking error here, truly speaking, it's very small and it will probably go away if you just add more elements to it, something that we call convergence. Okay, so that was a lot. This, as I said, this was going to be the most mathematically intense of lectures, and I hope I was able to explain to you not all the mathematics, but at least the motivation behind what we were doing and how the component Dalbar model was derived. Now, if you recall from module 2, where we looked at the analytical methods, I had taken time, some lectures out in module 2 to actually solve several examples. The reason was fairly simple. In module 2, we had analytical solutions. Analytical solutions can be solved with a calculator, they can be solved with a spreadsheet, they could be solved by hand if you dare do such mathematics. But the problem with the module 3 part, why in module 3 I haven't devoted a lot of time to solving problems, is because these problems are genuinely not possible to solve by hand. So the finite element method, for example, when I teach the finite element method, I always encourage students to program this out on a computer. You do not actually learn the finite element method by writing these equations and trying to solve things by hand. First of all, the equations are too big to solve by hand. You only really learn it when you start programming it on a computer. So what we're going to do in the next lecture, which is lecture 22, and lecture 22 is going to close up module 3. Lecture 22, I'm going to introduce you to a modern software called IceLab 2005. IceLab 2005, the name tells you it was made in 2005, so roughly 20 years ago at this point. IceLab 2005 was actually a software which was developed to implement everything that we've just talked about. So we talked about the MCZ elements for slabs. We talked about the component Dalbar model for Dalbars across joints. All of those things come together in this very well packaged program called IceLab 2005. So you don't actually have to know a lot of this background. As I'll show in IceLab 2005, it's just a couple of buttons you have to press, and it takes very little time for the solution to reach. And then you can solve all these systems for realistic problems and actually calculate the stresses, displacement, whatever you're interested in. So in the next lecture, I will show you a preview of IceLab 2005 and show you some of its capabilities, and I'll show you one very important thing that I've been talking about, that as the number of elements increase, the error should be decreasing. This is something we call convergence of the solution, and I will illustrate that point. Instead of solving a very large system on a slide, which it's not possible to do, I will use IceLab to solve it, and I will demonstrate to you this exact point on convergence of the system. So we will meet in the next lecture, lecture 22, and go over IceLab 2005. Thank you.